I will now show you how to allocate memory for your own variables at runtime. This is called dynamic memory allocation. This will happen in a new location in memory named the heap. So far, we've seen variables stored in a location named the stack. This location is for so-called automatic duration variables that come and go as functions or blocks or entered and exited. As you know, automatically allocated variables only persist during their own block or function. Dynamically allocated memory, on the other hand, is explicitly managed, so allocated and freed, by the user from the so-called heap. In C, the function to ask for memory is called malloc, as in memory allocation, and is part of the standard library stdlib. So in order to be able to use this malloc function, we need to #include this library. So we type #include, and then it's stdlib.h, standard library. Just like we normally include the standard input-output library if we want to use printf and scanf, we need to include the standard library if we want to include something like malloc. Next, because I want to use a visualization tool again, I'm going to add our show memory command, and you might notice that I'm putting in a different starting address than I normally do. This is because I want to visualize the heap this time rather than the stack, because I want to show you where dynamic memory is allocated. So let's start with this very, very simple command. Let's simply say I want to call this malloc function, malloc, memory allocation, and let's just put a 4 in there, as in I want to allocate space in the size of 4 bytes. Let's see what happens in memory when I do that. So we'll compile, and then we'll run this code step by step. You see the memory visualization showing up, and it's showing up somewhere in the middle of the memory. So after this malloc command is called, various things happen. I'm going to move the memory strip so that it's right in the middle. So you see a block of red, then a block of white, another block of red. The white block in the middle is the one that was actually reserved for me. So from memory location 104 to 107. That's what malloc reserved for me. But to the left of that block, something happened, as well as to the right of that block. What precisely happens there depends on your personal architecture and implementation. So here I show you how our implementation works. To the left of the 4 bytes that were reserved via malloc, you see 4 more bytes, and the number 8 is stored in there. That 8 indicates that we're reserving space for malloc, and then another 4, those are the 4 right spaces to the right of the space that were reserved. Okay. To the right of the 4 bytes that are reserved via malloc, you see another 4 bytes and some random number in there, EEF9. It's a hexadecimal number, and it indicates how much free space is remaining in the heap. So if I move this memory visualization over, you see there's lots and lots of free memory remaining. I'll move it back over here. So this number simply indicates how much memory is remaining so that subsequent calls of malloc know how much space there actually is left. So what would happen if I added another malloc command right after the first one? Where would that go? Let's try that out. We're going to compile and run this code step by step. Again, the first malloc shows up just as before. And now watch what happens when the next malloc is executed. We now still have the memory allocation from 104 to 107. That's from our first malloc. And then from 108 to 10b, remember this is all hexadecimal, we have now an 8 stored in there, indicating that the next 8 bytes are used for my next malloc. So again, we have the 4 bytes from 10c to 10f that are reserved via the second call of malloc, and then next to it how much space is now remaining, which is a little bit less than what we had remaining beforehand. So far, I've only used multiples of 4 for malloc. What if I use a different size? If I just wanted to reserve 1 byte, let's change it to malloc of 1. Compile and run. or it looks exactly the same as before. This is a bit architecture dependent, but in our architecture, malloc only reserves space in multiples of 4. So if you ask for less than 4, you will still get a multiple of 4. So instead of just 1 byte being reserved, 4 bytes have to be reserved, and so everything looks exactly the same in memory as it did before. All right, what if I ask for 5 bytes? See what happens then. Compile and run step by step. Well, 5 again is not a multiple of 4, so instead 8 bytes were reserved, because 8 is the nearest multiple of 4 to 5 that is bigger than 5. Now the number to the left is now an OC. Remember, it's a hexadecimal number. It stands for 12, meaning that 12 bytes are really used up here. 8 for the malloc of 5 that I called for, and another 4 to indicate how much space is remaining. And then when I call malloc again, I see the same picture over to the right. 8 bytes are reserved instead of just 5, and then how much space is remaining afterwards. All right. Now, typically, you wouldn't put a direct number into the malloc function. Rather, you would use the size of function to reserve space for the type of variable that you actually wanted to store in that space. So suppose you wanted to store an integer, then you would put in here size of int in order to get just the right amount of space to store an integer. And suppose you wanted to store an int and maybe also a double. Then for the next one, you would store size of double, and that's the amount of memory that will be reserved. Let's take a look at what happens. So first a call of malloc of size of int. Integers on our system take up 4 bytes. Again, this is system dependent, but on our system it's 4 bytes. So you see 4 bytes being reserved. However, doubles take up more space, and so 8 bytes are reserved for this double that's stored next to that integer. Similarly, I could say, well, I really want to store 3 integers. So then you could type 3 times size of int. And I want to store, let's say, 4 doubles, so I could type 4 times size of double. Let's see what happens now. So 3 times size of int. Each integer takes up 4 bytes. 3 times 4 is 12. So from 104 to 10f, that's actually 12 bytes. So 12 bytes were reserved to store these 3 integers. To the left of that whitish looking block, you see a 10 stored in those 4 bytes to the left. 10 is hexadecimal. It's really the decimal number 16. And 16 bytes were needed altogether to store my 12 bytes for the 3 integers, and the extra 4 bytes to indicate how much memory is remaining. Now let's see what happens when I ask for space for those 4 doubles. Each double takes up 8 bytes. 8 times 4 is 32. So when we allocate that memory, space for 32 bytes is reserved. That's a lot of space right there. And then to the right, we see how much memory is left. And to the left, we see the hexadecimal number 24, which really stands for 32 plus 8 in decimal. All right, so that's great. We have now understood how to ask for space in memory to store integers, doubles, and whatnot. But how do I actually access these memory locations? I need to store the address of where malloc found that space in some kind of variable. And what variable is good for that type? Well, we need a pointer. So for example, if we wanted to store where my integer space is reserved, I need an integer pointer. So int star is a pointer to an integer, the address of an integer, and let's call it the int ptr as an integer pointer. Similarly, if I wanted to store the address of where that double can live, I should use a double pointer, and I'll call it double ptr. And I'm just going to get space for 1 integer and 1 double here just to make life a little easier. So malloc actually returns a pointer that contains the address of that location where the block starts that malloc reserved. And so I can simply type here int ptr equals malloc size of int. Int ptr will then contain the address of where the location is in memory that has been reserved for me. Similarly, I can write double PTR equals malloc size of double, and that will then hold the memory location of where the space is for the double that I asked for. But there's one little thing here. Just to be a good citizen, one should always cast malloc to the correct data type. You see, there are two calls of malloc here, this one and that one. And for the top line, we're asking for an integer pointer because we want to store that in int ptr. For the second line, we want to call for a double pointer. So malloc, we're asking malloc to do two different things. And to make malloc's life easier, it's good to indicate that. So we're asking for an integer pointer here, whereas on the second line, we want a double pointer. And that's called casting to the correct data type. It's just being a good citizen to actually do so. Let's see what happens when we run this code. So our integer pointer is declared, but where did it go? I don't really see it anywhere. Well, it turns out, remember, variables are stored in the stack. But with the show memory command starting at 272, I'm showing you the heap of the memory locations. If I wanted to see the stack, so where this variable integer pointer lives, I would have to scroll all the way to the right, all the way. That's taking so long, I'm just going to hit this little arrow that shifts all the way to the right. And there indeed you see, there's my integer pointer, my space that can hold the address of an integer. Right now it doesn't hold an address because I haven't given it an address yet. Let's go back to the left. So this is my heap. And next I'm declaring my double pointer. That's also all the way to the right. I'm quickly going to go back there. Double PTR now exists. And then I'm going to go back to the left with my arrow. And next, I'm going to execute this instruction. Integer pointer is malloc of size of int. So malloc went ahead and reserved the space from 104 to 107 and supposedly stored that address, 104 hopefully, in my integer pointer. So let's check it out. I'm going to hit the arrow that points to the right to get to the stack. There's my integer pointer, and indeed, 104 is stored inside it. So the address of where the space is that malloc allocated is stored in integer PTR so that we can later on access it. Similarly, next, my double pointer has a new value, namely what malloc returns for size of double. And let's look at it, it's 10C. Let's go back to the heap. And indeed, at 10C is the space that starts for my double that was reserved via malloc. So now we have a pointer that points to the memory location that was reserved for us. Once we have a pointer, we can access it. We know how to do that. So let's quickly do that, and then we'll be done here. After my integer pointer gets the value that malloc spit out, I can now access that by dereferencing that pointer. I go to the location pointed to my integer pointer. That's the location that malloc reserved for my integer, and I can put something in there, suppose a 5, for example. And let's do the same thing for my double pointer. I can dereference my double pointer, and I can put something in there, let's say 9.0. Let's run this and see what happens. So again, my integer pointer is declared, double pointer is declared. My integer pointer gets the value 104, which is the address of the space that was reserved via malloc. And now I say star int ptr equals 5. So I'm going to the location pointed to by integer pointer. Integer pointer contains the address 104. So that space that you see in white there is now going to be addressed and changed. I'm going to store a 5 in there. And there it is. 5 showed up in the location from 104 to 107. Similarly, my double pointer now gets a value. Double pointer, as we saw before, has the value 10C. And now I'm dereferencing double pointer. I'm going to the place in memory where double pointer points to. I'm going to put a 9 in there. Now that doesn't look like a 9, but it's 9 in double format. So remember, a double is not an integer number, it's a decimal, and those are stored very differently in memory. That's why that doesn't really look like a 9 at all. So now you understand how to reserve space in memory and how to even put something in there. Very important is that you also need to release that space once you're done, and we'll learn that in a subsequent video very shortly. So Because you are now responsible for getting your own memory, it won't be destroyed automatically. You are responsible for doing that. We'll learn that shortly.